Hi, my name is Ronit Gandhi. I am a senior mathematics and biochemistry student at the University of Nebraska-Lincoln. And in the last few years, I've been researching the application of Markov chains in biology. And my project is utilizing Markov chains to estimate allele progression through generations. So, the basic idea starts with Punnett squares, which is familiar to pretty much everybody in the field. They teach it now in like 6th grade classrooms. So the Punnett squares are obviously utilized to predict probabilities for offspring based off the genotypes of parents. So on the left side of the screen over here, you can see the various genotypes, different Punnett squares, and the probabilities that are associated with them, which is just kind of information I'll be using later on. But right now, like the basis of this is based on Hardy-Weinberg equilibrium. Hardy-Weinberg equilibrium is also taught pretty much everywhere, and it's the basis of a lot of genetics. However, once you get far enough into the field, which is just honestly like a year or so, you realize how ineffective it actually is just because of the various rules associated with it. Like, you have to have random mating, no mutation, no migration, no natural selection, and a large sample size. And as we all know, it's very, very rare to find that in common biology. So for my model, it starts with that, but we very quickly phase it out. So it's more of just a support for it. But leaning more towards the math side, where the basis of this is Markov chains. So Markov chains are mathematical models that are used to estimate the path of a unit using only probabilities of the given options at a given time. So one basic example of it is the sunny-rainy Markov chain. So the sunny and rainy are different states or different areas where you could be. So imagine every day I wake up at 8 a.m., I look out my bedroom window and see if it's sunny or rainy. So say today I do that, I notice it's sunny. So now I'm at this state, and I think, okay, so tomorrow it could be sunny again with a 0.8 chance, or it could be rainy with a 0.2 chance. So second day comes by, I wake up, I look at my window, I see it's sunny again. So I know I win with that 0.8 chance. And then say the next day comes by, look outside and it's rainy. So that was that 0.2 chance. So now I'm at that rainy place. And now I could check my window the next day and it could be rainy again or it could be sunny. So that's what Markov chain is. It just gives you a different, like a model that is based off of different states rather than just one single long model. So a more complex example is the one below it. It becomes more complex. I'm looking at, say I start at 1 and I want to know where to go. So either I go to 2, 3, or stay at 1. Once I go to 2, then I can go to 1, 3, 4, stay at 2. Say I go to 3, then I can go to 1 through 3, 4, or 5. So it becomes a lot more intense. It becomes an infinite model. Now, infinite models are cool and all, but they're not very helpful because we have plenty of those laying around. If we want an infinite model, we wouldn't have this idea. So the reason that we're using Markov chains specifically is because of the hitting times that they have. Hitting times is using the probabilities and the progression of that unit. You get a single number, a single value that estimates how long it would take for the unit to reach a certain point. And that's what hitting times are based on. So now I can see how long it would take me to get from, say, point 1 to point 4. It could take, say it takes me 8 rounds. So I could go based off of different times, but on average it takes me 8 rounds to get there, 8 steps or 8 time frames. In that case, it tells me that the overall model or the situation I have is kind of leaning away from being at the 4th point. However, if it only takes me on average 3 jumps or 3 time frames, then I know it's based on the probabilities of the model, it pushes a lot more towards the 4. So that's the idea behind it. And that's why I apply it to genetics. So over here on the left is my Hardy-Weinberg model. So that's the one I started with. And all the equations, all the values are all based off of Hardy-Weinberg equilibrium. So the idea is I want to see how many time frames, how many generations it takes me to start from RR, little r, the homozygous recessive, and get to a homozygous dominant. That would signal to me how long it takes for my recessive allele to eventually get canceled out. So in Hardy-Weinberg with the random mating and stuff like that. And based off of the equation that's given up here, I could get the probabilities based off just the population parameters that are given. This gives me a model. It tells me how long it would take. However, as I mentioned before, it's not very helpful due to Hardy-Weinberg equilibrium being essentially useless, to be frank. So the idea is that we are going to go with this model. This one accounts for different biases, where gamma, alpha, and beta are all the biases, and they would sum up to 3. But when multiplied by the actual population sizes, or the distribution of the different genotypes, they all add up to 1. This creates a parameter to keep it all in check and make sure you don't have any extraneous values. But then this model tells us how long it would take to get that homozygous recessive allele to a homozygous dominant, make it how long it takes for the recessive allele to get canceled out. The idea is if it gets canceled out very quickly, then it's time for the ecologist or whoever is studying this to step in and change something about the population. This gives them kind of a number. It's similar to equated to like a pH value, where it's just an arbitrary number that kind of tells you, that measures a part of the solution or part of the situation that you're given, and you could use that to move on and create changes. So these are the equations that's based off of, and with this model you'd be given certain values, and it also helps to account for how not all biases are one-sided. For example, for peacocks, it's more one-sided because the more colorful of a male, the higher chance of mating. So it kind of pushes towards the color, which is a dominant trait. However, for in Africa, there was a growth of malaria, but there was also a high chance of someone being born with sickle cell anemia. Sickle cell anemia is a recessive homozygous illness that decreases life expectancy. However, having just one of the alleles for it, so being heterozygous, increases your immunity to malaria without having most of the negative effects that are associated with sickle cell anemia. So you could have different sides to it. It becomes a lot more intense, and that's where the model becomes a lot more helpful. So this could be applied to many different situations, and the idea isn't for it to be some kind of solution or a fix, but it's more a tool for an ecologist to use. And none of this would have been possible without the help of Austin Need, Dr. Clay Kresterler, and Dr. Bo Dang from the Department of Mathematics, Biological Sciences, and Mathematics at the University of Nebraska-Lincoln. And if you have any other questions, please feel free to either visit me at the conference or contact me at either of these sites, or at my email or LinkedIn. Well, thank you for listening, and yeah, have a nice day.